All right, so we're doing this one, ED204, a format string vulnerability. And this is one of the more bizarre things about C. I can bring this Linux command shell up here. Okay, so here I made a program ED204.C. All right, now there's no subroutine. All right. And there is a buffer with room for 1024. And actually, in principle, you could overrun it, but we're not going to do that. We're going to use much less than that. All we're going to do is take a command line argument. You see it here, argc star argv. That's how you do it in C. So argv1 is the command line argument that you execute it with. And all it's going to do is copy that into the buffer, which is plenty big, and then print the buffer. Then print a carriage return, and that's it. So it wouldn't be obvious immediately that there's any flaw in this program at all, at least for command line arguments that aren't longer than 1,000 characters. So if you run this, it should just print back the character I feed in as a command line argument. So I give it this, and if I put in hello, it echoes back hello. So everything seems fine. However, the problem is when you do a print command in C, you are supposed to have a format string telling it how to print it. This really ought to have a format string before it specifying like this here. This is the correct way to make a printf statement in C. You have a format string which tells it how to format the data, and then you have variables here. And so the way this tells it to format that variable as a string with the %s modifier. This kind of print is allowed by C. It will choose some default format, but it's dangerous, as you'll see. So if I were to put a format string here, like %x, then it prints hello, and then it prints something in hexadecimal. This is where you have to understand how C works. The way C works, and you can see it in the assembly code, is when you call a function, first it pushes all the arguments onto the stack, and then it jumps into the function. The function then looks on the stack expecting to find arguments. So when I put in this format string, it didn't notice that it had a format string and no variable, like it probably should have, like I think friendlier languages like Rust probably would. I'm not quite sure if Rust is immune to this, but I imagine it is. What it did is it jumped into the printf routine, and the printf routine just looked on the stack, and whatever it found there, it figured that must be the variable it was passed in. So I now have an information disclosure vulnerability. I'm now printing data that the developer did not intend for me to see, and I can put as many of these as I want to and just pump a lot of data off the stack. So you can see things you're not supposed to see. So that's pretty exciting. But what's even more exciting is you can take over the box. And you do that with the %n command. The %n format string has, I cannot imagine what the actual value of this is. But what the %n format string does is cause a segmentation fault. And remember, that's our clue that we have a memory corruption vulnerability here. %x takes whatever address it finds, whatever data it finds on the stack, and just prints it. %n takes whatever value it finds on the stack and it writes to that memory location. I don't know why you would want to do this, but it does. So I just wrote to these random memory locations until I wrote somewhere that was illegal, and that caused the segmentation fault. Now, so now I know I can execute a write operation to an address that's on the stack, but can I control what's on the stack? And the answer is I can, because this data I'm entering is going on the stack. So to find it, I put in some data I can spot, like AAAA, and then I put in some %x's. And I'll put a dot after each one just to make it easier to see the gap between them. Put a few of them in. And see, here's the 4 A's I put in. And there they are on the stack. They're just a few words down. So I have one word of junk, another word of junk, another word of junk, and the fourth word is under my control. So if I inject something with 3% X's and then a %N, I can control the address it writes to. So that's the joy of this format string vulnerability. We now control a parameter, and now we need to choose a RAM location to write to that will give me control of the box. And the way to do that is to go into the debugger. Well, you can also see it right here, by the way. If you just look at your source code, point C, you can observe here is where the exploit happens. When it prints this buffer without a format string, I'm able to trick that into writing somewhere in memory. And then after that, it does another printf, and then it does an exit. So what I'm going to do is hijack this call to exit. I can write to a relocation record in memory, which is used by the running program to find the standard C libraries. I can write to that and redirect a call to the exit library to go to an address of my choice. That's what we're going to do. And you can see that in the assembly code if you debug it. And then disassemble main. You'll see the assembly code that wrote this. There's a lot of push and stuff. And then there is a call print. And then there is a call exit. So you can see it calls the printf routine, and then it calls the exit. And this PLT is the procedure linkage table. And we're going to corrupt that. So, and here's the string copy, printf, put char, exit. All right, there's an exit up there. It's probably, that's not the one that's going to matter. That was the one that would happen under other conditions. Here it does the string copy. Here's the print without the format string. This is where the exploit happens. This is the single character to put the carriage return. And this is the exit at the end of the program. So if I corrupt the address of exit at this point, it will use it at that point. And now I need to find out where those things are stored. And you do that with the objdump function. Objdump lets you look inside executable code, and -R shows you the relocation records. So this shows me where the offsets are for the functions that are used, which is print, string, copy, exit, and put char. So the exit function is here. So if I change the address at that location, I will change where it goes when it's trying to implement the exit routine. So now I know that address. Now I just need to write to that address. All right, and to do that, I just need this. I'm going to copy this one line. Well, let's see, I'm going to have to copy a few of them. So go back in the debugger. All right. And now here I can examine that relocation record. So I just examine one word have hexadecimal. So there it is. This is the correct location, 0804-8366. That is an address that will really go to the real exit routine. But if I run this exploit, this is going to run my program with that string. And you should look familiar. This is that address backwards, 14A00408. Here's the address I want to write to. And then I have %X, 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 %N. Because I remember this address I put in will appear as the 4 words later on the stack. So I need to skip 3 words and then write to that address. That should put something else in that address. So I run that. Then the program crashes, where it tried to go to an address all zeros except for 14 at the end, which is blatantly illegal. And that's what was written there, the 14. So I can see what address I've written by where the program crashes. And this number is so small because the way the %N format works is it writes to the address that it finds on the stack, and the number it writes there is equal to the number of characters you have printed so far. And I haven't printed very many characters, so it's 14 in hexadecimal. So now there are a variety of other, so we just need to write a series of exploit programs. And I'm just going to use 2 windows here under the same server to make it easy. So if I look at the first one is F1. So now I want to write 4 times. So I'm going to write on byte 14, 15, 16, and 17. It'll do 4 separate writes biting. So I'll write all 32 bits by writing. Now, each time I write, it writes 32 bits, but most of the leading ones are zeros, since I'm not planning to have, millions of characters. So I'll just do a write here and then do a write one over, which will look another bit. So by doing 4 successive write operations, I can fill in this 32-bit word, and I will have some collateral damage, damaging the word after this, but I'm not using that, so it doesn't matter. So that's what will happen if I run this program on F1. So that'd be $./f1.py. That'll be running that exploit code. Yes. All right, and now you see, here's where it ended, 30, 38, 40, 48, because it printed, here's the exploit, junk, 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 and then random, there's the things it printed out. So the point is, this fills it in with that strange number, which is the number of bytes printed. And by next time I printed 8 more and 8 more and 8 more. So I'm now able to fill all 32 bits of the target address, but I'm still filling it with random illegal stuff. So to improve that, I go to F2. And here I have my information. I choose a target address, AABBCCDD. And I calculated the right number of bytes to add to the length of my string, multiples of 256, and those bytes, and then a correction factor I just determined by trial and error. And then I was able to control the length of those so that the total number of characters will have a lower byte equal to the number I've chosen. So I'm targeting this address, AABBCCDD, just to see if I really have control of it. So if I run with the F2 and run it again, you can see it printed a lot more characters, because it's printing like up to 255 characters before each one of the codes to mean more total characters have been printed. But you see it worked. I ended up at AABBCCDD. So now I can control the data I put in as well as the address I'm putting in there. All right. Now, I need to figure out what value to target. And that's F2. All right, so now to figure out what address to target, I need to make a more complete exploit. And this is another reason I wanted to show you this one. Let's look at F3. All right. Now, so this part of the code is going to write onto this address, this value into a relocation record, which will eventually go into the instruction pointer. Now I need to add exploit code. So here's my dummy exploit code. The NOP sled, a 90 is a no operation, an assembly language instruction that does nothing. A CC is a break. It's an assembly language instruction that will stop execution and return back to my debugger. So the NOP will do nothing, and the break will go back to the debugger, so I'll be able to see it's working. And I just want to make it big enough. This is big enough to hold standard shellcode, 100 bytes of NOP and 250 bytes of CC. That's enough room. So I'm going to write all that stuff. And this is all the part that makes the buffer, makes the format string vulnerability corrupt memory. And I'm just going to put my executable code on the stack. Now, not every program and not every operating system will allow you to run code on the stack. But if I'm lucky, this one will allow it, which is the old-fashioned way to do it. I can just put my executable code on the stack and then jump to that address and run it. So that's what this is testing. So that's F3. So I run F3. Say yes. All right, now you see it's longer. This is all this junk here is the stuff I had to write these 4 bytes AABBCCDD. This is the NOP sled and the breaks, unprintable characters. That's my dummy shellcode. Now it crashed at AABBCCDD because I just jumped to this random invalid address because I don't know what address to jump to. But now I can find out. With X120X ESP, I can look at the stack. And on the stack, here is my dummy shellcode. There's the NOP sled, and here's a lot of breaks. And so I just need to pick an address in the NOP sled instead of AABBCCDD. If I jump to any address here, it will then execute NOP, 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 break. So the only reason I did this dummy case was to learn these addresses. And you can see one of the ones in the middle is here at CFDC. That would be a good place to jump. So that's what the next one does, which is F4. And you see it here, CFBC is what I chose. And I guess I chose this one, which is just as good. Anywhere in the NOP sled is fine. So I'm going to, instead of writing that dummy value, AABBCCDD, I'm writing this value, which will hit one of the NOPs. And all the rest of it is unchanged. So when I run that one, F4, and say yes, now it did not crash. Let me go back and show you what happened last time. When you ran this one, it ended with a segmentation fault and an invalid memory in the instruction pointer, which was AABBCCDD. Now, it did not have a segmentation fault. It just hit a breakpoint trap, which is what I expected. So I jumped into my NOP sled and I ran the code. I ended up at D005. Let's see if that looks right by looking at the stack. So here's my NOP sled. And see, this is CFFC. This word starts 4-letter, 4 bytes after that, which is CF. It's D. This is D1000 right here, D1000, and this is D1004. 0, 1, 2, 3, and 4. So it hit 4 and broke at that point, and the next instruction is D1005. So I have succeeded in executing these commands and the first one of these, and then it stopped. So now I know I'm able to execute code, because if I weren't, it would have stopped back here. And I know where to put the code. Now all I have to do is create shell code and add it. But there is another problem that I have to overcome first. And that is dealing with bad characters. Real shell code has to be runnable machine language, which uses a lot of different bytes. And I'm inserting these bytes into a command line argument, which is a string. And there are certain characters that will break the string, like a space and a tab and a line feed. So I need to check for those bad characters. Now, obvious ones that you can guess would almost certainly be bad are tab, line feed, carriage return, and space. So I wrote a program, bad.py. Let me bring it up live here. A cat, not car. All right, this will put in the NOP sled, and then instead of the other shell code, it's going to just put in all possible bytes, except it's skipping the null byte and 9, 10, 13, and 32. So I have a string of all those bytes, and the only point of this is I can see whether they actually get there. If any of the bytes are forbidden, they will break the string and they will not get injected. So if I run bad.py, all right, it runs, and then it has a segmentation fault, of course, because I didn't control the address. I was jumping to an address with the NOP sled, but now I can examine the stack again. And so here's my NOP sled, and here's my dummy shellcode. Now it's 1, 2, 3, 4, 5, 6, 7, 8, and so on. So it made it to 17, made it to 28, 38, 48, 58, 68, 78, 89, A, B, C, D, and I have to go a little further, D8, E8, F8, all the way up to F, D, E, F, F. So there's my string of bytes going all the way from 0, 1 up to FF with no problem. So I have proven that there are no other bad bytes. I can use all of them except those 4. Now, I just need shellcode that does something fun. And the easiest way to do that is to use Metasploit. MSF Venom is a Metasploit tool, free tool. You can download it at any operating system, and you can make it code. I'm going to make it for 32-bit Linux code, which is what I'm using here. And I'm going to do shell bind, which will just open a listening port. And anybody that connects to that port will be able to execute command line commands. I tell it to skip these bad characters, the ones I found, 0, 9, 10, D, and 20. This prepend fork equals true makes it run better. I don't really understand why. And I want it in Python code. So you run this command with MSF Venom, and it writes the Python code for you. So then you just have to include that instead of the dummy shell code. And that's going to be my F5. So let's take a look at that. All right, this is the completed format string exploit. It uses 4 format strings exploits to write these bytes one at a time to spell out this address, FFFFCFBC, and that address points to inside this NOP sled, and then it will execute this code that came from Metasploit. So I write the NOP sled and then the buffer, and then I put enough padding at the end to keep the total length of it always the same, which is a good practice. So that should work. That's F5. So I run that one. Say yes. And notice it doesn't crash at all. Detaching, it had a fork, which opened a child process, and then it exited normally. It didn't crash at all. This is the NOP sled. This is the code from Metasploit with a bunch of unprintable characters. And here's the padding at the end to make the total length the same. So it finished, and you can tell it finished because if you do netstat minus pant, you can see there is a new process here listening on port 4444. And that is a Metasploit shellcode. You can connect to it from any server that can reach this one. I can do it locally with Netcat. And now you have a shell. You can do ID. It tells you who you are. You can do LS. You now have a remote shell. You can connect over the network and execute commands on here. You now have command injection, which is your goal. So that's why I structured the class this way. You start learning how to use command injection, and all these exploits are the steps how to get command injection through more and more complicated vulnerabilities. So that's how by just having one print statement that misses the format, you give me complete control of your box. All right. I'm going to stop this one.